Hello everyone and welcome to today's webinar, Unlocking the Possibilities of 3D Measurement, brought to you by Reliability Connect. My name is Alexa Cogburn, the Media Specialist for Mobius Connect, and I'll be your moderator for this session. First, I'd like to introduce today's presenter, Tony Planamento from Advanced Mechanical Enterprises. But before we get started, I'd like to review some important information with you. This webinar is being recorded and you will be emailed a link with access to the on-demand version of this webinar later. The recording of the webinar will also be shared on Reliability Connect, so feel free to pass it along to your colleagues if they weren't able to join us today. So Mobius Institute is a worldwide provider of reliability improvement and condition and monitoring education dedicated to supporting plants and helping them become safer and more successful. Mobius Institute's key advantage is its unique training style that features innovative 3D animations and software simulations, making complex topics easier for you to understand. The Mobius Institute Board of Certification is an ISO-accredited certification body that provides globally recognized certification to CBM practitioners and reliability professionals at any stage in their careers. To view our global training schedule, please visit www.mobiusinstitute.com. Next up, I'm pleased to share with you the Mobius Connect community platform. The Mobius Connect community is about you, providing you with the space and technology to connect with the right people and resources to help you solve problems, continue learning, and share your experience. Once you've created your free profile, similar to how you would on LinkedIn or any other professional networking site, you can start connecting with other industry professionals wherever you are in the world in any language. Mobius Connect includes fun features like the industry's live feed, forum discussions, interactive connection finder map, direct messaging, customized communications based on your areas of interest, global events, jobs, and news listings, and a mobile app which is available for download in the Apple and Google Play stores. You can also continue your educational journey live with Connect conferences or online with the Connect knowledge base. Or you can become a member of your regional community Connect group to gain access to additional resources and attend live or virtual meetups with professionals from your area. You can get started by creating your free profile and joining the community at www.mobiusconnect.com. I hope to see you there. And last but certainly not least, today's webinar is produced by Reliability Connect, the leading online educational community which is published by thought leaders and experienced industry professionals from all over the world. With a dedicated focus on each of the reliability improvement technologies, Reliability Connect allows you to organize content based on your areas of interest, like asset strategy, condition monitoring, continuous improvement, defect elimination, implementation strategy, data analytics, IIoT, leadership, precision, and proactive skills, and work in spares. You can get started on Reliability Connect by creating your free profile on Mobius Connect and selecting which technologies you'd like to stay up to date with. You can visit www.reliabilityconnect.com directly to access hundreds of on-demand webinars, interviews, videos, white papers, and more. Furthermore, if you're interested in contributing to the Reliability Connect knowledge base, please reach out to us during this webinar through the question panel, and we'll be happy to share more of that information with you. And now it is my pleasure to introduce today's presenter, Tony Planamento. Tony, how are you doing?
Hey, Alexa, I'm doing great, thanks. How are you?
I'm doing really well. Thank you for asking. And for those of you just joining us, welcome to Unlocking the Possibilities of 3D Measurement. If anyone does have any questions throughout the webinar, go ahead and type them in the question panel of your screen. And at the end of today's session, Tony will be more than happy to answer some of those questions for you. Your questions will be answered anonymously on air, so no need to worry about getting called out. If we run out of time and don't get to your question, Tony will reach out to you directly after the webinar to make sure that your questions are answered. All right, I'm going to go ahead and pass the presentation over to you now, Tony.
Thanks so much. Good afternoon, everyone. Like Alexa said, my name is Tony Planamento. I am the Technical Project Supervisor for Advanced Mechanical Enterprises. We also go by AME Solutions. We are We are a mechanical reliability services company specializing in predictive preventative maintenance of reciprocating and rotating machinery, predominantly in the marine industry, but we do deal quite a bit in the industrial sector as well. A little bit about myself. I graduated from the University of Central Florida with a mechanical engineering degree, bachelor's. And I've been with this company now for a little under 8 years. Started off as a field service engineer and kind of worked my way up into management and loving every minute of it. So today we are here to talk about 3D measurements and what it can do for you guys, your plants, your products, etc. Predominantly, we're going to go through some case studies. I have three major ones, and mostly in the industrial sector. There's two industrial, so there's one pumping component, there's one pumping station, and then we have one tugboat that we actually measured on. So the first one we're going to get into is the 3D survey of a formed suction intake and discharge column assembly. A little bit of background on this. There was a fabrication company who made these products, and it was not matching and lining up with the manufacturer's drawings. They were then sent to another fabricator who essentially corrected them. And because of the issues that they had been having, they reached out to us and we went out and verified all of the dimensions. So this right here is the formed suction intake. Everything highlighted here, I'm not sure how well it's coming up on your screens, but everything highlighted there was a measurement that they asked us to verify. And just a little bit more information, excuse me. This is actually for a submersible pump. The pump is going to go inside of the discharge column, and then they have anti-rotation ribs inside of that to keep the motor from rotating while it's operating. So like I said, this is the formed suction intake. And then the next slide here is going to show you a picture. So right there on the left is that full assembly. Give you a little bit of scale. These are two people on the right and then one of my colleagues on the left. It's probably about 10 feet tall overall. So they requested the overall height from the base to the very top of the discharge column there. And then on the right-hand side there, you'll see this is what the CAM2 software was going to look like after we did all of our measurements and constructions. So we took all of the measurements, and in that, so we take, it allows you to do all types of 3D geometrical shapes. So circles, planes, you can construct lines, you can measure lines, you can do best fit of all these shapes. You can do spheres, rectangles, all that good stuff. And so once we took all the measurements of the, again, formed suction intake on the right here, this is what it looks like. So we take the measurements and then we would establish what we call a coordinate system. So that tells us, what is going to be our origin point and then our X, Y, and Z directions based off of what it is we're actually trying to measure. So it's very customizable, very, very powerful software. From there, it also has the ability to construct what we call a level plane. So it measures level to the ground and it projects that plane out. And then from all that, we can do all kinds of stuff with constructing and measuring angles, lengths, dimensions, a lot of GD and T type stuff. So we can do runouts, we can do parallelism, flatness, plumbness, all that good stuff. This right here is some of the measurement data. So all the measurement points, let me go back here. So all the measurement points here are in red. You got 1, 2, 3, 4, 5, and then down at the bottom left is 6, 7, 8, so on and so forth. And those all correspond to this measurement table here. So we put all of our measured distances, what the distances were supposed to be in accordance with the drawing, and then the deviation. And we submitted all of this information to the manufacturer for approval to deploy into the field, essentially. So this is the second component. So the first picture actually showed the full assembly. This piece is actually the one that goes on top. And this is called the discharge column. And again, all the points 15, 16, 17, and 18. All the highlighted distances, those are our nominals. And that's what we're shooting for. And these right here are the results. So 15, 16, 17, and 18, the distances we measured, the distances that the drawing called out, and the deviations from those nominal values. Then you can see here on the right-hand side, that is how it looks in the CAM2 software. So we measured that inside barrel as a cylinder, and that's what you see there, standing upright. Some of you guys will notice that that piece is that little square piece with the round edges. If you look at the drawing, you'll notice that they actually asked for a round disc, and that was the diameter that they were asking for. So we measured those rounded corners and then measured it as a circle. And then you'll see that that circle right up at the top there. And that's how we did that one. So this is our, excuse me, this is our laser tracker. This is the equipment that we were using for all of these case studies. It is made by a company called Faro. And this actually has the ability to move positions. So you're able to change your reference by establishing reference points in the quote unquote world, and then measure that before you start taking any measurements. And then if you do end up having to move the device, you can key back into those reference points, and it will then reestablish where it is in that world before you start taking more measurements. So the reason I bring that up is because you can see here the way it's staged, we're only going to be able to measure that one side. So what we did is we actually measured reference points all around it, took those reference points in space, and then moved the device to the other side where those bolt holes are in the back there. And that's how we measured the bottom faces. These are a couple more of the points that we needed to take. So it was asking for the diameter of the bolt holes, the angle between the bolt holes, and all that good stuff. And then this little picture right here on the left is going to show the motor inside of that discharge column. So what was kind of nice about this is we actually did have to advise on some corrections. So I'm not sure how well you guys can see it, but inside of that cylinder, there's a flange face. And that flatness call out was actually out of spec. So we worked with the fabrication shop to machine down the high areas and then remeasured it until it was satisfactory. And that was pretty much the only error that we were able to identify in accordance with the manufacturer's drawing. And they, as far as I know, they delivered it successfully to the client. Okay, so second case study is at an actual pumping station. So some of the background on this one, the piping is about 10 feet in diameter. It's a very large pump. And they were having structural cracks form in the piping. So the pump station, or excuse me, the pump manufacturer's representative reached out to us to try and confirm some of the drawings or some of the dimensions from the drawings. So they took out all of the pump, all of the bearings, all of the impeller shafting, the impeller. So the impeller sits right inside of that big flange right there. Then it had some couple of pedestal bearings at those. I don't know if you can see in the green foundations where that little U shape is. And then there was another pedestal bearing at the green closest to the picture. So we ended up having to measure some flatness of each individual bearing foot. And then we had to measure that flatness to a best fit plane of all 4 feet to establish that there's no saw foot going on. They asked us to measure the plumbness of that flange as well as the discharge flange. And there's also these bolt hole locations on that flange, and there was also some dowel pins in that flange to align everything. So this is kind of what the whole setup looked like in the CAM2 software. You can see the suction flange is right there on the right, and then we've got our 4 bearing foundation feet right there, and then the best fit plane of all 4. Then you've got the discharge flange, which is at a 45-degree to the suction. And yes, we were able to measure that. Okay. So this is a picture kind of from the other, looking the other direction. So that's the discharge flange going down at a 45-degree angle. So we measured the flatness of all those flanges. We measured the plumbness of the suction flange. That is myself taking the measurements. And I am about 6 feet tall, so you can see that's about 10 feet in diameter, roughly. It's very interesting having to wear a harness to climb up a flange. So yeah, we measured the plumbness of that flange itself. And then we measured the locations of all of the bolt holes. So if you look over there on the table on the right, you've got your center X, center Y, and center Z. That is the center point coordinates to the origin of the suction flange itself. So the X is actually going to be looking into the screen. Our Y is going to be side to side. That would be our normal X if we're looking at a 2D. And then our Z would be our actual Y coordinate system in the 2D plane here. This is another measurement that they requested that we make. This is another key feature to this software and what it's able to unlock essentially. So what it was asking for was the distance from the suction flange to the discharge flange. And what we did was we constructed a dimension from that center point to the center point at the 45-degree incline there. And then, not sure how well it's coming up on the screen, but you can actually see we've got our actual distance measured there. That was 235.840. And then our nominal was actually 236 inches. So again, same thing. We took all of our measurements. We established our coordinate system based off of what our plane of interest is. And then we were able to use those GD and T features in the software to establish flatness, perpendicularity, parallelism, of all of our features of interest, so to speak. And then we were able to compile all of this into a report and present it to our customer. And again, happy customer, happy end product. Okay, and the last case study that I have right now is we were working on, we got a call from a partner of ours who works heavily in the commercial marine industry. And there was a tugboat that ran aground. It hit bottom. And these tugboats have something called azipod thrusters. So it's essentially a transmission going into a down right angle gear. And then that shaft goes into another right angle gear that the propeller gets mounted to. So it sticks quite far down into the water. And unfortunately, this vessel did hit the bottom. So what they did was that's the boat right there. So they took the thrusters, which would normally be on that upslope in the back of the boat there. They took that completely out as a unit and transferred it to a local machine shop. And then they broke down the individual components. So we measured the flange of the hull that the whole assembly mounts to. They wanted the inner diameters and the flatness of those flanges. That's on the right there. That's us taking the measurements on the flanges. So we mounted the tracker at the bottom there. And then we had to use a little cherry picker there to get somebody up there. And being a laser, it was challenging getting some line of sight stuff there. So then we moved everything over into the local machine shop and do the best I can to explain this. So on the bottom right hand side of that left picture, that is going to be the mounting flange that goes up into the vessel. So, and then where you see that inside machine surface, that is where the transmission flange bolts to. And that's what the transmission is supported on. And then the piece that my colleague is measuring on the stepladder there, that is they simply called it a cone, and that cone mounts to the bottom of that flange that's on the bottom right of that picture. So again, we're measuring flatness, diameters, bolt hole diameters, and locations. And then they were actually very interested in the parallelism from the planes of the top of the cone versus the bottom of the cone. And the reason that is of interest is because of the bearings that go into those housings. And if those bearings are cocked, as most of you that are watching and are vibration analysts, it will show up as a cocked bearing. Not a whole lot you can do about a cocked bearing if it's in a cocked housing. Again, this is the hull flange and what it's going to look like in the CAM2 software. We basically just measured it as a plane and then a circle for the inside diameter. And then we measured several bolt holes. Actually, I think we measured all of the bolt holes. It was quite a bit. We constructed a best fit circle to all of the bolt holes to establish that diameter as well. All right, so this is the drawing of the cones that I was referring to. So you can see it's very conical in shape, and all of the blue arrows are the circles or the cylinders that they asked us to measure. And they wanted us to give them runouts, diameters of all the circles and cylinders. And then they wanted us to provide flatness and perpendicularity and parallelism of all of the planes, which are the red arrows. And that was all in reference to, I believe, that P1 at the top right, left there. Excuse me. So inside there, if you look at the blue arrow, the C4, that is going to be where one of the bearings seat. So when the vessel hit bottom, the force, their concern was that the force deformed that flange up at the top, which is that P1. And that can cause a whole lot of problems when it's running. Okay. So like I mentioned in the first case study, this equipment allows us to move locations to gain line of sight to every aspect of the component. So if you could see in the surrounding structure, there's a few beams, structural beams that we were able to mount our reference points to. And again, we measured that before we took any measurements. And we took the initial set of measurements on the picture in the left. It was one, two, I believe 3 planes. And then in order to get the other side, which is the picture of the right, on the right, excuse me, we had to move the device and tie back into our reference points so that it could calculate its position in the world. Okay. This is what it looks like in the Cam2 software. You can see that not we didn't actually measure the cone itself, so that's why you can't really see it, but you can see the larger circles and the larger squares, which are the planes, in reference to the smaller circles and the smaller squares on the left of the top picture, which is going to be at the small end of the cone. Okay. This is the mounting flange that I mentioned. So the cone seats to that P1. Then it's got that, excuse me, it's got another mounting surface on that P2 there. And then on the top, P3 is where the transmission would mount to. And that is actually piloted, which is why they had us measure the C3 there. And again, we were measuring the flatness, perpendicularity, and parallelism of the planes, as well as the diameters and runouts of the circles and cylinders labeled in blue there. This is how we had to have the flanges staged in order to measure them. You can see that outside is that P1, and then we had the P2 on the inside there. And then the P3 is on that right-hand picture on the backside. And that's representation of it in the Cam2 software. You can see the circles and the cylinders, as well as the planes represented as squares there. And what was interesting in this, and I don't have a visual aid on it for this, but the Faro laser tracker actually has an integral thermocouple that plugs into it. And that thermocouple is constantly reading the environmental conditions of the area that you're measuring in. So this particular area was, while it was covered, it was still outdoors and it was not climate controlled. And what was very helpful was we were able to look and see what the actual temperature was while we were making this measurement. And the manufacturer came back on our initial report questioning some of the diameters of what we measured and saying that it just wasn't possible in reference to their drawing. So after digging back into the software and kind of doing a deep dive into the data, we were able to determine that the drawing, so some people may not know this, I know I didn't at the time, but when you're looking at a technical drawing of a component, all of the dimensions, unless it's stated otherwise, are assumed to be taken at 20 degrees Celsius. So at the time where we were measuring, it was anywhere from 30 to 32 degrees Celsius. Quite a significant temperature differential. And what was very powerful and impactful on this software is we were able to establish our coordinate systems, and it has a material thermal growth compensation. So by knowing what the temperature was at the time of the measurement, and then having the ambient temperature, well, not ambient, excuse me, that's the wrong term, but having the known temperature of 20 degrees Celsius as a starting point from a technical drawing, and then by telling it what the material is, it can actually calculate thermal growth based off of, again, that coordinate system that is established. And once we did that, it actually brought the numbers much, much closer to what the drawing was and what their tolerances are. Um, Unfortunately, these were uh, slightly damaged, and they are now currently being machined at the site of our partner who brought us in. And it's still in progress. So hopefully we'll have an update on that fairly soon. um, so that is actually the end of all the case studies I have prepared. I would like to, however, show another application that we've used this quite a bit on, specifically in bore alignment on ships. It is also applicable to crankshafts in an engine, camshaft bores in an engine. But Alexa, if you don't mind, I could stop sharing this and share that.
The question screen?
No, I just want to share one more
Oh, okay.
report. Yeah.
Okay. Yeah, go ahead. 1 second.
All right, that's the one there.
Alrighty.
So this was an alignment report and dimensional verification for a 360-foot steel vessel that we were working on. So we had the laser tracker mounted in a support stand that was welded to the hull. Because it was steel and it was fluctuating from fairly warm temperatures to fairly cold temperatures, believe it or not, it deviated about 9 millimeters from noon to midnight. So all of these measurements were taken overnight to minimize the effects of thermal growth on the hull from the sun. So this was mounted aft of the strut, and it shot into the stern tube, the aft end, and then the forward end, and then went up into a line shaft bearing, excuse me, two line shaft bearings, right up to the transmission flange, all the way at the front there. We were also asked to do some dimensional verifications, and that is, if you look here, that's our port rudder post and starboard rudder post. And then these were the center lines and other areas that they asked us to measure heights to. These are the alignment results. This was the other side here. So we measured both rudders on the one file because they asked us to do the distance between the two. And then for this one, we actually only needed to do the one. These were the results there. This right here were the dimensional verifications that they asked us to check. So we did our targets, the deviation from the targets, the target measurement being our nominal values. And then they wanted to measure the shaft center line to level, all that good stuff. And with that, Alexa, I think that's all I got. We can open it up to questions if you want.
Perfect. Yes, just like Tony said, we are going to open the floor up for some questions. You guys can go ahead and put your questions in the question panel on your screen, and we will have Tony answer those for you. So we'll give them a couple more minutes, but for right now, we do have one question, Tony. Is this equipment more for quality control of individual components or measurements of the overall production line?
Yeah, that's a good one. So the short answer is both. The tracker itself, when you're not using components or accessories, is more for the actual production line, the overall outline, arrangement, machinery arrangement for the area. It gives you a lot of geometrical measurements. Your flatness of the foundation, how level it is, how plumb things are, alignment of certain components. But there are other pieces of equipment and accessories of the tracker that allow you to drill down into that component level. Specifically, they have a scanner, a 3D scanner, which can be converted into CAD files and real dimensional values of the overall design in a CAD file. And then the tracker has something called a ferrule arm, which is on a 6 degree of freedom, one of those little robotic arms, but you're actually controlling it. And it looks like a gun, and you're kind of moving it around and measuring the little nooks and crannies of each component that the tracker might not catch on its own by itself.
Okay, well, thank you for explaining that. We did have someone send in a statement question. I'm not really sure. Maybe you can help me break it down. Someone said, I had an experience with a vertical pump on a hydrocarbons transporter vessel. The vibration was perpendicular to the axis of the pump motor assembly. The fitting of the motor with the pump was irregular, causing induced mechanical stress. So maybe they're asking, what do you think about that situation?
It was perpendicular to the shaft line, and then what was that last part?
The fitting of the motor with the pump was irregular, causing induced mechanical stress.
Okay, so without seeing what that looks like, I would imagine that the motor is bolted to the pump itself. I could be mistaken there, but if that is indeed the case, and the flanges may have been cast incorrectly or machined incorrectly, and maybe they're kind of angled like that, that would certainly cause something to that effect, and that is something that could be measured with the 3D measurements. Obviously, they would have to be taken apart, but it is something that can be measured.
Good to know. That's probably what they were asking. So next question, Tony. Can this be used for digital twins?
Yes. So not sure who watching has had any experience with this, but I know a lot of the reliability field is kind of moving in this direction, the IIoT and Industry 4.0. A lot of which is running digital twins where you create essentially a copy in a CAD file, and you start subjecting it to some of the strains and stresses that you may be experiencing through normal through your normal operation cycles. So a lot of times what will happen is somebody will design these components in a CAD program, and then that they start the process of applying those real world strains and stresses to it, but they never really go back and get any type of additional feedback. So what these measurements can do is essentially you get your CAD file programmed, and then you can actually go out and measure these components versus the design versus the fabrication and the as-built dimensions, and then you can start feeding that information back into your digital twin program, as well as you could do this in multiple stages. So you could do it from the build, that's your baseline, that's your baseline condition. And then say 3-6 months down the road, maybe you want to see if something is moving or something is not as it was built, perhaps. I'm not 100% sure on that, but this would allow you to go out there and either with the scanner or more accurately with the tracker, put those geometries back into your program.
Great, thank you. We do have another question. How adaptable is the mounting/setup of the equipment?
So as delivered, it comes with standard with a space grade aluminum tripod that allows you to go, up and down to a certain extent. But they do have several accessories. So in that pumping station case study, for example, they had something they call an extension neck, and that was about 20 inches long. So that can actually thread onto that tripod, and then the tracker would go on top of that, and that allows you to go a little bit higher up, which allowed for line of sight to the bottom of that discharge flange that we measured. They also have magnetic bases, very strong electromagnets that you can engage with just a little Allen key. Quarter turn, it engages and it locks onto a anything metal, right? Anything magnetic, and it's I don't know what the pull force of the magnet is, but it is very strong, and that allows you to kind of get in there on low profile things. So, give an example of that one. I was measuring the bore alignment of a cargo ship, and they were doing some line boring of the aft stern tube, and they fabricated this bracket with 4 pieces of square tube welded to the barrel itself, and then they had a little table at the bottom that I was able to mount the magnetic base on and put the tracker head in there and get it right underneath their line boring bar, and we use that to align the bearings of the line boring bar. Excuse me 1 second, sorry. They also have a kind of counterweight assembly. We don't actually have this one just yet. We haven't come across the need for it, but where you are able to mount it offset from the bracket, and it's got a little counterweight on the back end to hold it stable, and that allows you, say, like you're trying to look down a hole, but you can only get your bracket over here, so you can stick it here and look down, and it's got a counterweight on the back end to keep it from toppling over. So yeah, I mean it's very adaptable, and they've got a lot of accessories that can allow you to measure just about anything, really.
Well, that's great to know. I'm sure a lot of the listeners loved hearing that more about that. All right, so Tony, it looks like we don't have any more questions at the moment. If anyone does have a question that comes to mind later, you can always email us at info@mobiusconnect.com, or go ahead and submit them into the question panel right now, and we'll get those to Tony later. But before we wrap things up for today, Tony, did you have anything else that you'd like to add?
Yeah, if anybody would like to reach out, again, we are Advanced Mechanical Enterprises. We are located in Fort Lauderdale, Florida, and we do just about everything. Vibration, infrared, alignment, machining, fabrication, pipe fitting, welding, excuse me. And we deal with just about everyone, honestly.
Great. Well, thank you, Tony, for your time and awesome presentation. And on behalf of the team here at Mobius Connect, thank you to our wonderful audience for joining us today as well. And just as a quick reminder, the recorded version of this webinar will be made available on Reliability Connect, and you'll also receive a link to the on-demand library in an email as well. You'll see a full list of upcoming webinars and other educational content on Reliability Connect, which you can visit directly at www.reliabilityconnect.com. And if you're interested in engaging with other industry professionals or would like to participate on the industry's live feed and ongoing forum discussions, you can do so by visiting Mobius Connect at www.mobiusconnect.com. And you can also follow us on social media at Mobius Connect to stay up to date with the latest community happenings. And if you have any questions at all, you can email us directly at info@mobiusconnect.com. Again, that's info@mobiusconnect.com if you have any questions from this webinar or any questions in general. Thanks again for joining us. Have a great day. Please stay safe, and we'll see you all next time. Bye.